A planet is an astronomical body orbiting a star or stellar remnant that is massive enough to be rounded by its own gravity, is not massive enough to cause thermonuclear fusion, and has cleared its neighboring region of planetesimals. The term planet is ancient, with ties to history, astrology, science, mythology, and religion. 5 planets in the solar system are visible to the naked eye. These were regarded by many early cultures as divine, or as emissaries of deities. As scientific knowledge advanced, human perception of the planets changed, incorporating a number of disparate objects. In 2006, the International Astronomical Union, IAU, officially adopted a resolution defining planets within the solar system. This definition is controversial because it excludes many objects of planetary mass based on where or what they orbit. Although 8 of the planetary bodies discovered before 1950 remain planets under the current definition, some celestial bodies, such as Ceres, Pallas, Juno and Vesta, each an object in the solar asteroid belt, and Pluto, the first trans-Neptunian object discovered, that were once considered planets by the scientific community, are no longer viewed as planets under the current definition of planet. Planets in astrology have a different definition. The planets were thought by Ptolemy to orbit Earth in deferent and epicycle motions. Although the idea that the planets orbited the Sun had been suggested many times, it was not until the 17th century that this view was supported by evidence from the first telescopic astronomical observations, performed by Galileo Galilei. About the same time, by careful analysis of pre-telescopic observational data collected by Tycho Brahe, Johannes Kepler found the planets' orbits were elliptical rather than circular. As observational tools improved, astronomers saw that, like Earth, each of the planets rotated around an axis tilted with respect to its orbital pole, and some shared such features as ice caps and seasons. Since the dawn of the space age, close observation by space probes has found that Earth and the other planets share characteristics such as volcanism, hurricanes, tectonics, and even hydrology. Planets are generally divided into 2 main types: large low-density giant planets, and smaller rocky terrestrials. There are 8 planets in the solar system. In order of increasing distance from the Sun, they are the 4 terrestrials, Mercury, Venus, Earth, and Mars, then the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune. 6 of the planets are orbited by 1 or more natural satellites. Several thousands of planets around other stars, extrasolar planets or exoplanets, have been discovered in the Milky Way. As of October 1, 2019, 4,118 known extrasolar planets in 3,063 planetary systems, including 669 multiple planetary systems, ranging in size from just above the size of the Moon to gas giants about twice as large as Jupiter, have been discovered, out of which more than 100 planets are the same size as Earth, 9 of which are at the same relative distance from their star as Earth from the Sun, that is in the circumstellar habitable zone. On December 20, 2011, the Kepler Space Telescope team reported the discovery of the first Earth-sized extrasolar planets, Kepler-20 and Kepler-20f, orbiting a Sun-like star, Kepler-20. A 2012 study, analyzing gravitational microlensing data, estimates an average of at least 1.6 bound planets for every star in the Milky Way. Around 1 in 5 Sun-like stars is thought to have an Earth-sized planet in its habitable zone. History. The idea of planets has evolved over its history, from the divine lights of antiquity to the earthly objects of the scientific age. The concept has expanded to include worlds not only in the solar system, but in hundreds of other extrasolar systems. The ambiguities inherent in defining planets have led to much scientific controversy. The 5 classical planets, being visible to the naked eye, have been known since ancient times and have had a significant impact on mythology, religious cosmology, and ancient astronomy. In ancient times, astronomers noted how certain lights moved across the sky, as opposed to the fixed stars, which maintained a constant relative position in the sky. Ancient Greeks called these lights pi lambda nu eta tau epsilon sigma sigma tau rho epsilon sigma, planetes asters, wandering stars, or simply pi lambda alpha nu tau alpha iota, plantae, wanderers, from which today's word planet was derived. In ancient Greece, China, Babylon, and indeed all pre-modern civilizations, it was almost universally believed that Earth was the center of the universe and that all the planets circled Earth. The reasons for this perception were that stars and planets appeared to revolve around Earth each day, and the apparently common sense perceptions that Earth was solid and stable and that it was not moving but at rest. Babylon. The first civilization known to have a functional theory of the planets were the Babylonians, who lived in Mesopotamia in the 1st and 2nd millennia BC. The oldest surviving planetary astronomical text is the Babylonian Venus Tablet of Amazonica, a 7th century BC copy of a list of observations of the motions of the planet Venus, that probably dates as early as the 2nd millennium BC. The Mo.Tapin is a pair of cuneiform tablets dating from the 7th century BC that lays out the motions of the sun, moon, and planets over the course of the year. The Babylonian astrologers also laid the foundations of what would eventually become Western astrology. The Enuma Enlil, written during the Neo-Assyrian period in the 7th century BC, comprises a list of omens and their relationships with various celestial phenomena, including the motions of the planets Venus, Mercury, and the outer planets Mars, Jupiter, and Saturn were all identified by Babylonian astronomers. These would remain the only known planets until the invention of the telescope in early modern times. Greco-Roman astronomy. The ancient Greeks initially did not attach as much significance to the planets as the Babylonians. The Pythagoreans, in the 6th and 5th centuries BC, appear to have developed their own independent planetary theory, which consisted of the Earth, Sun, Moon, and planets revolving around a central fire at the center of the universe. Pythagoras or Parmenides is said to have been the first to identify the evening star, Hesperos, and morning star, Phosphoros, as one and the same, Aphrodite, Greek corresponding to Latin Venus, though this had long been known by the Babylonians. In the 3rd century BC, Aristarchus of Samos proposed a heliocentric system, according to which Earth and the planets revolved around the Sun. The geocentric system remained dominant until the scientific revolution. By the 1st century BC, during the Hellenistic period, the Greeks had begun to develop their own mathematical schemes for predicting the positions of the planets. These schemes, which were based on geometry rather than the arithmetic of the Babylonians, would eventually eclipse the Babylonians' theories in complexity and comprehensiveness, and account for most of the astronomical movements observed from Earth with the naked eye. These theories would reach their fullest expression in the Almagest written by Ptolemy in the 2nd century CE. So complete was the domination of Ptolemy's model that it superseded all previous works on astronomy and remained the definitive astronomical text in the Western world for 13 centuries. To the Greeks and Romans there were 7 known planets, each presumed to be circling Earth according to the complex laws laid out by Ptolemy. They were, in increasing order from Earth, in Ptolemy's order and using modern names, the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Cicero, in his De Natura Deorum, enumerated the planets known during the 1st century BC using the names for them in use at the time. But there is most matter for wonder in the movements of the 5 stars, which are falsely called wandering, falsely, because nothing wanders which through all eternity preserves its forward and retrograde courses, and its other movements, constant and unaltered. For instance, the star which is farthest from the Earth, which is known as the star of Saturn, and is called by the Greeks Phi Alpha Theta Omega Nu, Phaenon, accomplishes its course in about 30 years, and though in that course it does much that is wonderful, first preceding the Sun, and then falling off in speed, becoming invisible at the hour of evening, and returning to view in the morning, it never through the unending ages of time makes any variation, but performs the same movements at the same times. Beneath it, and nearer to the Earth, moves the planet of Jupiter, which is called in Greek Phi Alpha Theta Omega Nu, Phaethon. It completes the same round of the 12 signs in 12 years, and performs in its course the same variations as the planet of Saturn. The circle next below it is held by Pi Upsilon Rho Epsilon Iota Sigma, Pyroeus, which is called the planet of Mars, and traverses the same round as the 2 planets above it in 4 and 20 months, All but, I think, 6 days. Beneath this is the planet of Mercury, which is called by the Greeks Sigma Tau Lambda Beta Omega Nu, Stilbon. It traverses the round of the zodiac in about the time of the year's revolution, and never withdraws more than one sign's distance from the Sun, moving at one time in advance of it, and at another in its rear. The lowest of the 5 wandering stars, and the one nearest the Earth, is the planet of Venus, which is called Phi Omega Sigma Phi Rho Omicron Sigma, Phosphoros, in Greek, and Lucifer in Latin, when it is preceding the Sun, but Sigma Pi Epsilon Rho Omicron Sigma, Hesperos, when it is following it. It completes its course in a year, traversing the zodiac both latitudinally and longitudinally, as is also done by the planets above it, and on whichever side of the Sun it is. It never departs more than 2 signs distance from it. India. In 499 CE, the Indian astronomer Aryabhata propounded a planetary model that explicitly incorporated Earth's rotation about its axis, which he explains as the cause of what appears to be an apparent westward motion of the stars. He also believed that the orbits of planets are elliptical. Aryabhata's followers were particularly strong in South India, where his principles of the diurnal rotation of Earth, among others, were followed, and a number of secondary works were based on them. In 1500, Nilakantha Somyaji of the Kerala School of Astronomy and Mathematics, in his Tantra Sangraha, revised Aryabhata's model. In his Aryabhatayabhasya, a commentary on Aryabhata's Aryabhataya, he developed a planetary model where Mercury, Venus, Mars, Jupiter and Saturn orbit the Sun, which in turn orbits Earth, similar to the Tychonic system later proposed by Tycho Brahe in the late 16th century. Most astronomers of the Kerala school who followed him accepted his planetary model. Medieval Muslim astronomy. In the 11th century, the transit of Venus was observed by Visa, who established that Venus was, at least sometimes, below the Sun. In the 12th century, Ibn Bajjah observed 2 planets as black spots on the face of the Sun, which was later identified as a transit of Mercury and Venus by the Maragha astronomer Qutb-al-Din Shirazi in the 13th century. Ibn Bajjah could not have observed a transit of Venus, because none occurred in his lifetime. European Renaissance. With the advent of the scientific revolution, use of the term planet changed from something that moved across the sky, in relation to the star field, to a body that orbited Earth, or that was believed to do so at the time, and by the 18th century to something that directly orbited the Sun when the heliocentric model of Copernicus, Galileo and Kepler gained sway. Thus, Earth became included in the list of planets, whereas the Sun and Moon were excluded. At first, when the first satellites of Jupiter and Saturn were discovered in the 17th century, the terms planet and satellite were used interchangeably, although the latter would gradually become more prevalent in the following century. Until the mid-19th century, the number of planets rose rapidly because any newly discovered object directly orbiting the Sun was listed as a planet by the scientific community. 19th century. In the 19th century, astronomers began to realize that recently discovered bodies that had been classified as planets for almost half a century, such as Ceres, Pallas, Juno, and Vesta, were very different from the traditional ones. These bodies shared the same region of space between Mars and Jupiter, the asteroid belt, and had a much smaller mass. As a result, they were reclassified as asteroids. In the absence of any formal definition, a planet came to be understood as any large body that orbited the Sun. Because there was a dramatic size gap between the asteroids and the planets, and the spate of new discoveries seemed to have ended after the discovery of Neptune in 1846, there was no apparent need to have a formal definition. 20th century. In the 20th century, Pluto was discovered. After initial observations led to the belief that it was larger than Earth, the object was immediately accepted as the 9th planet. Further monitoring found the body was actually much smaller. In 1936, Ray Littleton suggested that Pluto may be an escaped satellite of Neptune, and Fred Whipple suggested in 1964 that Pluto may be a comet. As it was still larger than all known asteroids and seemingly did not exist within a larger population, it kept its status until 2006. In 1992, astronomers Alexander Wolszczyn and Dale Frail announced the discovery of planets around a pulsar, PSRB 1257+12. This discovery is generally considered to be the first definitive detection of a planetary system around another star. Then, on October 6, 1995, Michel Mayor and Didier Queloz of the Geneva Observatory announced the first definitive detection of an exoplanet orbiting an ordinary main sequence star, 51 Pegasi. The discovery of extrasolar planets led to another ambiguity in defining a planet, the point at which a planet becomes a star. Many known extrasolar planets are many times the mass of Jupiter, approaching that of stellar objects known as brown dwarfs. Brown dwarfs are generally considered stars due to their ability to fuse deuterium, a heavier isotope of hydrogen. Although objects more massive than 75 times that of Jupiter fuse hydrogen, objects of only 13 Jupiter masses can fuse deuterium. Deuterium is quite rare, and most brown dwarfs would have ceased fusing deuterium long before their discovery, making them effectively indistinguishable from supermassive planets. 21st century. With the discovery during the latter half of the 20th century of more objects within the solar system and large objects around other stars, disputes arose over what should constitute a planet. There were particular disagreements over whether an object should be considered a planet if it was part of a distinct population such as a belt, or if it was large enough to generate energy by the thermonuclear fusion of deuterium. A growing number of astronomers argued for Pluto to be declassified as a planet, because many similar objects approaching its size had been found in the same region of the solar system, the Kuiper Belt, during the 1990s and early 2000s. Pluto was found to be just one small body in a population of thousands. Some of them, such as Quaoar, Sedna, and Eris, were heralded in the popular press as the 10th planet, failing to receive widespread scientific recognition. The announcement of Eris in 2005, an object then thought of as 27% more massive than Pluto, created the necessity and public desire for an official definition of a planet. Acknowledging the problem, the IAA set about creating the definition of planet, and produced one in August 2006. The number of planets dropped to the 8 significantly larger bodies that had cleared their orbit: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, and a new class of dwarf planets was created, initially containing 3 objects: Ceres, Pluto and Eris. Extrasolar planets. There is no official definition of extrasolar planets. In 2003, the International Astronomical Union, IAU, Working Group on Extrasolar Planets issued a position statement, but this position statement was never proposed as an official IAA resolution and was never voted on by IAA members. The positions statement incorporates the following guidelines, mostly focused upon the boundary between planets and brown dwarfs. Objects with true masses below the limiting mass for thermonuclear fusion of deuterium, currently calculated to be 13 times the mass of Jupiter for objects with the same isotopic abundance as the Sun, that orbit stars or stellar remnants are planets, no matter how they formed. The minimum mass and size required for an extrasolar object to be considered a planet should be the same as that used in the solar system. Substellar objects with true masses above the limiting mass for thermonuclear fusion of deuterium are brown dwarfs, no matter how they formed or where they are located. Free-floating objects in young star clusters with masses below the limiting mass for thermonuclear fusion of deuterium are not planets, but are sub-brown dwarfs, or whatever name is most appropriate. This working definition has since been widely used by astronomers when publishing discoveries of exoplanets in academic journals. Although temporary, it remains an effective working definition until a more permanent one is formally adopted. It does not address the dispute over the lower mass limit, and so it steered clear of the controversy regarding objects within the solar system. This definition also makes no comment on the planetary status of objects orbiting brown dwarfs, such as 2M1207b. One definition of a sub-brown dwarf is a planet mass object that formed through cloud collapse rather than accretion. This formation distinction between a sub-brown dwarf and a planet is not universally agreed upon, Astronomers are divided into two camps as whether to consider the formation process of a planet as part of its division in classification. One reason for the dissent is that often it may not be possible to determine the formation process. For example, a planet formed by accretion around a star may get ejected from the system to become free-floating, and likewise a sub-brown dwarf that formed on its own in a star cluster through cloud collapse may get captured into orbit around a star. One study suggests that objects above 10 Jup formed through gravitational instability and should not be thought of as planets. The 13 Jupiter mass cutoff represents an average mass rather than a precise threshold value. Large objects will fuse most of their deuterium and smaller ones will fuse only a little, and the 13 megajoules value is somewhere in between. In fact, calculations show that an object fuses 50% of its initial deuterium content when the total mass ranges between 12 and 14 megajoules. The amount of deuterium fused depends not only on mass but also on the composition of the object, on the amount of helium and deuterium present. As of 2011, the extrasolar planets encyclopedia included objects up to 25 Jupiter masses, saying, "The fact that there is no special feature around 13 Jup in the observed mass spectrum reinforces the choice to forget this mass limit." As of 2016, this limit was increased to 60 Jupiter masses based on a study of mass-density relationships. The Exoplanet Data Explorer includes objects up to 24 Jupiter masses with the advisory, "The 13 Jupiter mass distinction by the IAA Working Group is physically unmotivated for planets with rocky cores, and observationally problematic due to this ambiguity." The NASA Exoplanet Archive includes objects with a mass, or minimum mass, equal to or less than 30 Jupiter masses. Another criterion for separating planets and brown dwarfs, rather than deuterium fusion, formation process or location, is whether the core pressure is dominated by Coulomb pressure or electron degeneracy pressure. 2006 IAA definition of planet. The matter of the lower limit was addressed during the 2006 meeting of the IAA's General Assembly. After much debate and one failed proposal, a large majority of those remaining at the meeting voted to pass a resolution. The 2006 resolution defines planets within the Solar System as follows. A planet, 1, is a celestial body that, a, is in orbit around the Sun, b, has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round, shape, and, c, has cleared the neighborhood around its orbit. 1. The 8 planets are, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Under this definition, the Solar System is considered to have 8 planets. Bodies that fulfill the first 2 conditions but not the third, such as Ceres, Pluto, and Eris, are classified as dwarf planets, provided they are not also natural satellites of other planets. Originally an IAA committee had proposed a definition that would have included a much larger number of planets as it did not include C as a criterion. After much discussion, it was decided via a vote that those bodies should instead be classified as dwarf planets. This definition is based in theories of planetary formation, in which planetary embryos initially clear their orbital neighborhood of other smaller objects. As described by astronomer Stephen Soter. The end product of secondary disk accretion is a small number of relatively large bodies, planets, in either non-intersecting or resonant orbits, which prevent collisions between them. Minor planets and comets, including KBOs, Kuiper Belt objects, differ from planets in that they can collide with each other and with planets. The 2006 IAA definition presents some challenges for exoplanets because the language is specific to the Solar System and because the criteria of roundness and orbital zone clearance are not presently observable. Astronomer Jean-Luc Margot proposed a mathematical criterion that determines whether an object can clear its orbit during the lifetime of its host star, based on the mass of the planet, its semi-major axis, and the mass of its host star. This formula produces a value π that is greater than 1 for planets. The 8 known planets and all known exoplanets have π values above 100, while Ceres, Pluto, and Eris have π values of 0.1 or less. Objects with pi values of 1 or more are also expected to be approximately spherical, so that objects that fulfill the orbital zone clearance requirement automatically fulfill the roundness requirement. Objects formerly considered planets. The table below lists solar system bodies once considered to be planets. Beyond the scientific community, Pluto still holds cultural significance for many in the general public due to its historical classification as a planet from 1930 to 2006. Mythology and naming. The names for the planets in the Western world are derived from the naming practices of the Romans, which ultimately derive from those of the Greeks and the Babylonians. In ancient Greece, the two great luminaries, the Sun and the Moon, were called Helios and Selene. The farthest planet, Saturn, was called Phaenon, the shiner, followed by Phaethon. Jupiter, bright, the red planet, Mars, was known as Pyroeus, the fiery, the brightest. Venus, was known as Phosphoros, the light-bringer, and the fleeting final planet, Mercury, was called Stilbon, the gleamer. The Greeks also made each planet sacred to one among their pantheon of gods. The Olympians, Helios and Selene, were the names of both planets and gods. Phaenon was sacred to Cronus, the Titan who fathered the Olympians. Phaethon was sacred to Zeus, Cronus's son, who deposed him as king. Pyroeus was given to Ares, son of Zeus and god of war. Phosphoros was ruled by Aphrodite, the goddess of love, and Hermes, messenger of the gods and god of learning and wit, ruled over Stilbon. The Greek practice of grafting their gods' names onto the planets was almost certainly borrowed from the Babylonians. The Babylonians named Phosphoros after their goddess of love, Ishtar, Pyroeus after their god of war, Nergal, Stilbon after their god of wisdom, Nabu, and Phaethon after their chief god, Marduk. There are too many concordances between Greek and Babylonian naming conventions for them to have arisen separately. The translation was not perfect. For instance, the Babylonian Nergal was a god of war, and thus the Greeks identified him with Ares. Unlike Ares, Nergal was also god of pestilence and the underworld. Today, most people in the Western world know the planets by names derived from the Olympian pantheon of gods. Although modern Greeks still use their ancient names for the planets, other European languages, because of the influence of the Roman Empire and, later, the Catholic Church, use the Roman, Latin, names rather than the Greek ones. The Romans, who, like the Greeks, were Indo-Europeans, shared with them a common pantheon under different names but lacked the rich narrative traditions that Greek poetic culture had given their gods. During the later period of the Roman Republic, Roman writers borrowed much of the Greek narratives and applied them to their own pantheon, to the point where they became virtually indistinguishable. When the Romans studied Greek astronomy, they gave the planets their own gods' names: Mercurius, for Hermes; Venus, Aphrodite; Mars, Ares; Iter, Zeus; and Saturnus, Cronus. When subsequent planets were discovered in the 18th and 19th centuries, the naming practice was retained with Neptunus, Poseidon. Uranus is unique in that it is named for a Greek deity rather than his Roman counterpart. Some Romans, following a belief possibly originating in Mesopotamia but developed in Hellenistic Egypt, believed that the 7 gods after whom the planets were named took hourly shifts in looking after affairs on Earth. The order of shifts went Saturn, Jupiter, Mars, Sun, Venus, Mercury, Moon, from the farthest to the closest planet. Therefore, the first day was started by Saturn, first hour; second day by Sun, 25th hour, followed by Moon, 49th hour, Mars, Mercury, Jupiter, and Venus. Because each day was named by the god that started it, this is also the order of the days of the week in the Roman calendar after the nundinal cycle was rejected, and still preserved in many modern languages. In English, Saturday, Sunday, and Monday are straightforward translations of these Roman names. The other days were renamed after Tuesday, Woden, Wednesday, Thunner, Thursday, and Frige, Friday, the Anglo-Saxon gods considered similar or equivalent to Mars, Mercury, Jupiter, and Venus, respectively. Earth is the only planet whose name in English is not derived from Greco-Roman mythology. Because it was only generally accepted as a planet in the 17th century, there is no tradition of naming it after a god. The same is true, in English at least, of the Sun and the Moon, though they are no longer generally considered planets. The name originates from the 8th century Anglo-Saxon word erda, which means ground or soil, and was first used in writing as the name of the sphere of Earth perhaps around 1300. As with its equivalents in the other Germanic languages, it derives ultimately from the Proto-Germanic word eartho, ground, as can be seen in the English earth, the German erd, the Dutch ard, and the Scandinavian jord. Many of the Romance languages retain the Old Roman word terra, or some variation of it, that was used with the meaning of dry land as opposed to sea. The non-Romance languages use their own native words. The Greeks retained their original name, Gamma, Ge. Non-European cultures use other planetary naming systems. India uses a system based on the Navagraha, which incorporates the 7 traditional planets, Surya for the Sun, Chandra for the Moon, Buddha for Mercury, Shukra for Venus, Mangala for Mars, Brihaspati for Jupiter, and Shani for Saturn, and the ascending and descending lunar nodes Ru and Ketu. China and the countries of Eastern Asia historically subject to Chinese cultural influence, such as Japan, Korea and Vietnam, use a naming system based on the 5 Chinese elements: water, Mercury, metal, Venus, fire, Mars, wood, Jupiter, and Earth, Saturn. In traditional Hebrew astronomy, the 7 traditional planets have, for the most part, descriptive names. The Sun is Hema or the Hot One, the Moon is Leva or the White One, Venus is Kakav Noga or the Bright Planet, Mercury is Kakav or the Planet, given its lack of distinguishing features, Mars is Medim or the Red One, and Saturn is Shetai or the Resting One, in reference to its slow movement compared to the other visible planets. The odd one out is Jupiter, called Tzedek or Justice. Stieglitz suggests that this may be a euphemism for the original name of Kakav Baal or Baal's planet, seen as idolatrous and euphemized in a similar manner to Ishbosheth from 2 Samuel. In Arabic, Mercury is Utarid, cognate with Ishtar, Astarte. Venus is Az-Zahara, the Bright One, an epithet of the goddess Al-Uzza. Earth is Alard, from the same root as Eretz. Mars is Al-Mirik, meaning featherless arrow due to its retrograde motion. Jupiter is Al-Mustari, the reliable one, from Akkadian, and Saturn is Zihal, withdrawer. Formation. It is not known with certainty how planets are formed. The prevailing theory is that they are formed during the collapse of a nebula into a thin disk of gas and dust. A protostar forms at the core, surrounded by a rotating protoplanetary disk. Through accretion, a process of sticky collision, dust particles in the disk steadily accumulate mass to form ever larger bodies. Local concentrations of mass known as planetesimals form, and these accelerate the accretion process by drawing in additional material by their gravitational attraction. These concentrations become ever denser until they collapse inward under gravity to form protoplanets. After a planet reaches a mass somewhat larger than Mars' mass, it begins to accumulate an extended atmosphere, greatly increasing the capture rate of the planetesimals by means of atmospheric drag. Depending on the accretion history of solids and gas, a giant planet, an ice giant, or a terrestrial planet may result. When the protostar has grown such that it ignites to form a star, the surviving disk is removed from the inside outward by photoevaporation, the solar wind, Poynting Robertson drag and other effects. Thereafter there still may be many protoplanets orbiting the star or each other, but over time many will collide, either to form a single larger planet or release material for other larger protoplanets or planets to absorb. Those objects that have become massive enough will capture most matter in their orbital neighborhoods to become planets. Protoplanets that have avoided collisions may become natural satellites of planets through a process of gravitational capture, or remain in belts of other objects to become either dwarf planets or small bodies. The energetic impacts of the smaller planetesimals, as well as radioactive decay, will heat up the growing planet, causing it to at least partially melt. The interior of the planet begins to differentiate by mass, developing a denser core. Smaller terrestrial planets lose most of their atmospheres because of the secretion, but the lost gases can be replaced by outgassing from the mantle and from the subsequent impact of comets. Smaller planets will lose any atmosphere they gain through various escape mechanisms. with the discovery and observation of planetary systems around stars other than the Sun, it is becoming possible to elaborate, revise or even replace this account. The level of metallicity, an astronomical term describing the abundance of chemical elements with an atomic number greater than 2, helium, is now thought to determine the likelihood that a star will have planets. Hence, it is thought that a metal-rich population I star will likely have a more substantial planetary system than a metal-poor population 2 star. Solar System. There are 8 planets in the Solar System, which are in increasing distance from the Sun. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Jupiter is the largest, at 318 Earth masses, whereas Mercury is the smallest, at 0.055 Earth masses. The planets of the Solar System can be divided into categories based on their composition. Terrestrials, planets that are similar to Earth, with bodies largely composed of rock, Mercury, Venus, Earth, and Mars. At 0.055 Earth masses, Mercury is the smallest terrestrial planet, and smallest planet, in the Solar System. Earth is the largest terrestrial planet. Giant planets, Jovians, massive planets significantly more massive than the terrestrials, Jupiter, Saturn, Uranus, Neptune. Gas giants, Jupiter and Saturn, are giant planets primarily composed of hydrogen and helium and are the most massive planets in the Solar System. Jupiter, at 318 Earth masses, is the largest planet in the Solar System, and Saturn is 1/3 as massive, at 95 Earth masses. Ice giants, Uranus and Neptune, are primarily composed of low boiling point materials such as water, methane, and ammonia, with thick atmospheres of hydrogen and helium. They have a significantly lower mass than the gas giants, only 14 and 17 Earth masses. Planetary attributes. Exoplanets. An exoplanet, extrasolar planet, is a planet outside the Solar System. As of October 1, 2019, there are 4,118 confirmed exoplanets in 3,063 systems, with 669 systems having more than one planet. In early 1992, radio astronomers Alexander Wolszczyn and Dale Frail announced the discovery of 2 planets orbiting the pulsar PSR 1257+12. This discovery was confirmed, and is generally considered to be the first definitive detection of exoplanets. These pulsar planets are believed to have formed from the unusual remnants of the supernova that produced the pulsar, in a second round of planet formation, or else to be the remaining rocky cores of giant planets that survived the supernova and then decayed into their current orbits. The first confirmed discovery of an extrasolar planet orbiting an ordinary main sequence star occurred on October 6, 1995, when Michel Mayor and Didier Queloz of the University of Geneva announced the detection of an exoplanet around 51 Pegasi. From then until the Kepler mission, most known extrasolar planets were gas giants comparable in mass to Jupiter or larger, as they were more easily detected. The catalogue of Kepler candidate planets consists mostly of planets the size of Neptune and smaller, down to smaller than Mercury. There are types of planets that do not exist in the Solar System, super-Earths and mini-Neptunes, which could be rocky like Earth or a mixture of volatiles and gas like Neptune. A radius of 1.75 times that of Earth is a possible dividing line between the two types of planet. There are hot Jupiters that orbit very close to their star and may evaporate to become Chthonian planets, which are the leftover cores. Another possible type of planet is carbon planets, which form in systems with a higher proportion of carbon than in the Solar System. A 2012 study, analyzing gravitational microlensing data, estimates an average of at least 1.6 bound planets for every star in the Milky Way. On December 20, 2011, the Kepler Space Telescope team reported the discovery of the first Earth-size exoplanets, Kepler-20 and Kepler-20f, orbiting a Sun-like star, Kepler-20. Around 1 in 5 Sun-like stars have an Earth-sized planet in the habitable zone, so the nearest would be expected to be within 12 light-years distance from Earth. The frequency of occurrence of such terrestrial planets is one of the variables in the Drake equation, which estimates the number of intelligent, communicating civilizations that exist in the Milky Way. There are exoplanets that are much closer to their parent star than any planet in the solar system is to the Sun, and there are also exoplanets that are much farther from their star. Mercury, the closest planet to the Sun at 0.4 astronomical units, takes 88 days for an orbit, but the shortest known orbits for exoplanets take only a few hours, for example Kepler 70b. The Kepler 11 system has 5 of its planets in shorter orbits than Mercury's, all of them much more massive than Mercury. Neptune is 30 astronomical units from the Sun and takes 165 years to orbit, but there are exoplanets that are hundreds of AU from their star and take more than 1,000 years to orbit, for example 1RXS 1609b. Planetary mass objects. A planetary mass object, PMO, planemo, or planetary body is a celestial object with a mass that falls within the range of the definition of a planet, massive enough to achieve hydrostatic equilibrium, to be rounded under its own gravity, but not enough to sustain core fusion like a star. By definition, all planets are planetary mass objects, but the purpose of this term is to refer to objects that do not conform to typical expectations for a planet. These include dwarf planets, which are rounded by their own gravity but not massive enough to clear their own orbit, the larger moons, and free-floating planemos, which may have been ejected from a system, rogue planets, or formed through cloud collapse rather than accretion, sometimes called sub-brown dwarfs. Dwarf planets. A dwarf planet is a planetary mass object that is neither a true planet nor a national satellite. It is in direct orbit of a star, and is massive enough for its gravity to compress it into a hydrostatically equilibrious shape, usually a spheroid, but has not cleared the neighborhood of other material around its orbit. Alan Stern, who proposed the term dwarf planet, has argued that location should not matter and that only geophysical attributes should be taken into account, geophysical planet definition, and that dwarf planets are thus a subtype of planet. However, the IAL classifies dwarf planets as a separate category. The number of dwarf planets in the solar system is unknown. IAL has recognized 3, Ceres, Pluto and Eris, and assigned the naming of 2 additional candidates, Haumea and Makemake, to the IAL Dwarf Planet Naming Committee. Rogue planets. Several computer simulations of stellar and planetary system formation have suggested that some objects of planetary mass would be ejected into interstellar space. Some scientists have argued that such objects found roaming in deep space should be classed as planets, although others have suggested that they should be called low-mass brown dwarfs. Sub-brown dwarfs. Stars form via the gravitational collapse of gas clouds, but smaller objects can also form via cloud collapse. Planetary mass objects formed this way are sometimes called sub-brown dwarfs. Sub-brown dwarfs may be free-floating such as CHA 110,913 773,444 and OTS 44, or orbiting a larger object such as 2-mass J04414489 plus 2301513. Binary systems of sub-brown dwarfs are theoretically possible. Of 162,225, 240,515 was initially thought to be a binary system of a brown dwarf of 14 Jupiter masses and a sub-brown dwarf of 7 Jupiter masses, but further observations revised the estimated masses upwards to greater than 13 Jupiter masses, making them brown dwarfs according to the IAL working definitions. Former stars. In close binary star systems, one of the stars can lose mass to a heavier companion. Accretion-powered pulsars may drive mass loss. The shrinking star can then become a planetary mass object. An example is a Jupiter mass object orbiting the pulsar PSR J17 1914-38. These shrunken white dwarfs may become a helium planet or carbon planet. Satellite planets. Some large satellites, moons, are of similar size or larger than the planet Mercury, for example Jupiter's Galilean moons and Titan. Alan Stern has argued that location should not matter and that only geophysical attributes should be taken into account in the definition of a planet, and proposes the term satellite planet for a planet-sized satellite. Captured planets. Rogue planets and stellar clusters have similar velocities to the stars and so can be recaptured. They are typically captured into wide orbits between 100 and 105 astronomical units. The capture efficiency decreases with increasing cluster volume, and for a given cluster size it increases with the host, primary mass. It is almost independent of the planetary mass. Single and multiple planets could be captured into arbitrary unaligned orbits, non-coplanar with each other or with a stellar host spin, or pre-existing planetary system. Attributes. Although each planet has unique physical characteristics, a number of broad commonalities do exist among them. Some of these characteristics, such as rings or natural satellites, have only as yet been observed in planets in the solar system, whereas others are also commonly observed in extrasolar planets. Dynamic characteristics. Orbit. According to current definitions, all planets must revolve around stars, thus, any potential rogue planets are excluded. In the solar system, all the planets orbit the Sun in the same direction as the Sun rotates, counterclockwise as seen from above the Sun's north pole. At least one extrasolar planet, WASP-17b, has been found to orbit in the opposite direction to its star's rotation. The period of one revolution of a planet's orbit is known as its sidereal period or year. A planet's year depends on its distance from its star. The farther a planet is from its star, not only the longer the distance it must travel, but also the slower its speed, because it is less affected by its star's gravity. No planet's orbit is perfectly circular, and hence the distance of each varies over the course of its year. The closest approach to its star is called its periasteron, perihelion in the solar system, whereas its farthest separation from the star is called its apastron, aphelion. As a planet approaches periasteron, its speed increases as it trades gravitational potential energy for kinetic energy, just as a falling object on Earth accelerates as it falls. As the planet reaches apastron, its speed decreases, just as an object thrown upwards on Earth slows down as it reaches the apex of its trajectory. Each planet's orbit is delineated by a set of elements. The eccentricity of an orbit describes how elongated a planet's orbit is. Planets with low eccentricities have more circular orbits, whereas planets with high eccentricities have more elliptical orbits. The planets in the solar system have very low eccentricities, and thus nearly circular orbits. Comets and Kuiper belt objects, as well as several extrasolar planets, have very high eccentricities, and thus exceedingly elliptical orbits. The semi-major axis is the distance from a planet to the halfway point along the longest diameter of its elliptical orbit, see image. This distance is not the same as its apastron, because no planet's orbit has its star at its exact center. The inclination of a planet tells how far above or below an established reference plane its orbit lies. In the solar system, the reference plane is the plane of Earth's orbit, called the ecliptic. For extrasolar planets, the plane, known as the sky plane or plane of the sky, is the plane perpendicular to the observer's line of sight from Earth. The 8 planets of the solar system all lie very close to the ecliptic. Comets and Kuiper belt objects like Pluto are at far more extreme angles to it. The points at which a planet crosses above and below its reference plane are called its ascending and descending nodes. The longitude of the ascending node is the angle between the reference plane's zero longitude and the planet's ascending node. The argument of periapsis, or perihelion in the solar system, is the angle between a planet's ascending node and its closest approach to its star. Axial tilt. Planets also have varying degrees of axial tilt. They lie at an angle to the plane of their star's equators. This causes the amount of light received by each hemisphere to vary over the course of its year. When the northern hemisphere points away from its star, the southern hemisphere points towards it, and vice versa. Each planet therefore has seasons, changes to the climate over the course of its year. The time at which each hemisphere points farthest or nearest from its star is known as its solstice. Each planet has 2 in the course of its orbit. When one hemisphere has its summer solstice, when its day is longest, the other has its winter solstice, when its day is shortest. The varying amount of light and heat received by each hemisphere creates annual changes in weather patterns for each half of the planet. Jupiter's axial tilt is very small, so its seasonal variation is minimal. Uranus, on the other hand, has an axial tilt so extreme it is virtually on its side, which means that its hemispheres are either perpetually in sunlight or perpetually in darkness around the time of its solstices. Among extrasolar planets, axial tilts are not known for certain, though most hot Jupiters are believed to have negligible to no axial tilt as a result of their proximity to their stars. Rotation. The planets rotate around invisible axes through their centers. A planet's rotation period is known as a stellar day. Most of the planets in the solar system rotate in the same direction as they orbit the Sun, which is counterclockwise as seen from above the Sun's north pole, the exceptions being Venus and Uranus, which rotate clockwise, though Uranus's extreme axial tilt means there are differing conventions on which of its poles is north, and therefore whether it is rotating clockwise or anti-clockwise. Regardless of which convention is used, Uranus has a retrograde rotation relative to its orbit. The rotation of a planet can be induced by several factors during formation. A net angular momentum can be induced by the individual angular momentum contributions of accreted objects. The accretion of gas by the giant planets can also contribute to the angular momentum. Finally, during the last stages of planet building, a stochastic process of protoplanetary accretion can randomly alter the spin axis of the planet. There is great variation in the length of day between the planets, with Venus taking 243 days to rotate, and the giant planets only a few hours. The rotational periods of extrasolar planets are not known. However, for hot Jupiters, their proximity to their stars means that they are tidally locked, that is, their orbits are in sync with their rotations. This means, they always show one face to their stars, with one side in perpetual day, the other in perpetual night. Orbital clearing. The defining dynamic characteristic of a planet is that it has cleared its neighborhood. A planet that has cleared its neighborhood has accumulated enough mass to gather up or sweep away all the planetesimals in its orbit. In effect, it orbits its star in isolation, as opposed to sharing its orbit with a multitude of similar-sized objects. This characteristic was mandated as part of the IA's official definition of a planet in August 2006. This criterion excludes such planetary bodies as Pluto, Eris and Ceres from full-fledged planethood, making them instead dwarf planets. Although to date this criterion only applies to the Solar System, a number of young extrasolar systems have been found in which evidence suggests orbital clearing is taking place within their circumstellar disks. Physical characteristics. Mass. A planet's defining physical characteristic is that it is massive enough for the force of its own gravity to dominate over the electromagnetic forces binding its physical structure, leading to a state of hydrostatic equilibrium. This effectively means that all planets are spherical or spheroidal. Up to a certain mass, an object can be irregular in shape, but beyond that point, which varies depending on the chemical makeup of the object, gravity begins to pull an object towards its own center of mass until the object collapses into a sphere. Mass is also the prime attribute by which planets are distinguished from stars. The upper mass limit for planethood is roughly 13 times Jupiter's mass for objects with solar-type isotopic abundance, beyond which it achieves conditions suitable for nuclear fusion. Other than the Sun, no objects of such mass exist in the Solar System, but there are exoplanets of this size. The 13 Jupiter mass limit is not universally agreed upon, and the Extrasolar Planets Encyclopedia includes objects up to 20 Jupiter masses, and the Exoplanet Data Explorer up to 24 Jupiter masses. The smallest known planet is PSRB 1257+12a, one of the first extrasolar planets discovered, which was found in 1992 in orbit around a pulsar. Its mass is roughly half that of the planet Mercury. The smallest known planet orbiting a main sequence star other than the Sun is Kepler 37b, with a mass, and radius, slightly higher than that of the Moon. Internal differentiation. Every planet began its existence in an entirely fluid state. In early formation, the denser, heavier materials sank to the center, leaving the lighter materials near the surface. Each therefore has a differentiated interior consisting of a dense planetary core surrounded by a mantle that either is or was a fluid. The terrestrial planets are sealed within hard crusts, but in the giant planets the mantle simply blends into the upper cloud layers. The terrestrial planets have cores of elements such as iron and nickel, and mantles of silicates. Jupiter,